PU2 champions, welcome to the today's episode of Dhurandhar series where we are going to decode the chapter alcohols, phenols and ethers. And let me tell you, this chapter is super important for your board exams, for your pre-board exams, as this chapter can straight away give you 10 marks, right? And the best part is the questions from this chapter are very simple, easy, direct and predictable. So in this particular video, I'm going to cover all the important methods of preparation, all the important reactions, name reactions, chemical properties, everything in just one video. So after watching this video, I'm pretty sure that you will understand this concept completely and you will not miss out on the 10 out of 10 from this particular chapter, right? So let's get started without any further delay. And yes, before starting, a small request, please do not forget to subscribe the channel, as this channel is going to be your ultimate guide for KCET and PU2 2026 examination. So let's see what we have in today's class. So first we'll talk about classification and nomenclature. So if you have understood the haloalkanes classification and nomenclature, it is pretty same to that. Next we'll talk about the structure, then we'll discuss about the preparation of alcohols, preparation of phenols, physical properties, chemical reactions of alcohols, chemical reaction of phenols, commercial alcohols, and lastly we'll talk about ethers. Okay, so first let us start with the classification. So the first criteria of classification is the number of OH groups. Okay, now alcohols are those compounds which have this OH functional group. Okay, and phenols are those where we have OH group attached to a aromatic ring, right? And the second classification is for the sp3 carbon COH bond, and the third classification is for sp2 COH bonds. Okay, now under so let us go one by one. So if you see for number of OH groups, if you have only one OH group, we call it monohydric. 2 OH we call it dihydric. 3 OH we call it trihydric. Okay, this is very simple. Now let's move to the sp3 COH bond. Now here we are talking about that carbon, okay, which is having 3 bonds. Okay, it is having 4 sigma bonds are present. If 4 sigma bonds are present, that means this carbon is sp3 hybridized. Now what are the conditions, or I can say the classification of a sp3 hybridized carbon? Now see, if this particular carbon which contains the OH group is attached to only one carbon, then it is a primary. If this is attached to 2 other carbons, then it is secondary. If it is attached to 3 other carbons, it is tertiary. Clear? Now we'll talk about allylic alcohols. So this is also very similar what we have already studied. So if the carbon containing the OH group is attached to a sp2 carbon, okay, this is a sp2 carbon and this is sp3 carbon, right? So this is allylic. But since now see, this particular carbon is attached to only one carbon, so being allylic is there, it is also primary. Now coming to the next one, this particular carbon, you can see it is having OH group and it is attached to an sp2 carbon. So it is definitely allylic, but with that it is also a secondary because it is attached to 2 other carbons. Now coming to this one, this OH group is attached to carbon, right? And then this is attached to an sp2 carbon, right? This is an sp2 carbon, so it is allylic. But apart from that, it is also a tertiary. So this is tertiary allylic, secondary allylic, and this is primary allylic. Now coming to benzylic alcohols. So when you have the CH2 group is attached to the benzene, and to that if OH is attached, then it is called primary group. Okay. Next, if you have I can say a benzene ring, okay, then it is attached to COH, and then again this carbon which is the benzylic carbon is attached to another carbon, then it is secondary. Now similarly, if you have this C and that benzylic carbon is attached to 3 other carbons, then it is tertiary. Clear? Next, we'll move to vinylic. Vinylic is for sp2 hybridized. So whenever a OH is directly attached to an sp2 carbon, sp2 carbon means the carbon which is having double bond, okay, then it is called a vinylic alcohol. And what are phenols? When OH group is directly attached to the benzene ring, we call it a phenol group. Okay, and here you can see this is monohydric because only one OH. Here we have 2 OH, so it is dihydric, and here we have 3 OH, so it is trihydric. Okay, next we'll talk about the classification of ethers. Now ethers are classified as symmetrical and asymmetrical. Now what is the structure of ether? See, you have R, O and R. Okay, now if both the R groups are same, for example here you can see this is also ethyl, this is also ethyl, that is called a symmetrical ether. Now, if you have this R groups are different. For example, here I have ethyl, here I have methyl, here you can see I have ethyl, here I have phenyl. Then these compounds or this type of, I can say, ethers are your asymmetrical ethers. Okay. Now we'll come to nomenclature. Now for alcohols, the suffix is OL. Okay, the suffix used is OL. Okay. Now for example, CH3OH is there. How will you name its IUPAC name? So it is one carbon. So I have methane, and the suffix OL stands for OH group. And the common name here is methyl alcohol. Next, if you have three carbons in one chain, then it is N-propyl alcohol or propane 1-OL. Now, if you have one OH group on the second carbon, then we call it as isopropyl alcohol or propane 2-OL. Next, we have all the four carbons in one chain, so it is N-butyl alcohol or butane 1-OL. And when you have all the four carbons in one chain and then you have a OH group, then it is called as sec-butyl alcohol or butane 2-OL. Okay. Now here you can see this particular group is called as isobutyl. Okay. So, or you can write down 3-methyl propane 1-OL, sorry, 2-methyl propane 1-OL, and this is isobutyl alcohol. Okay. So I just want you that you must remember isopropyl alcohol, N-butyl, secondary butyl, and this isobutyl. Okay, these structures, the common names are more popular than the IUPAC name. So make sure that you understand their common names and the structure. Similarly, you have tert butyl alcohol. Okay, now when you have two CH2 groups and to both of them OH groups are attached, then we call it as ethylene glycol. And if three OH groups are there, sorry, if three OH groups are there, then we call it as glycerol. Okay, just a minute. Yeah. Okay, three OH groups you can see here, carbon 1, carbon 2, and carbon 3. Then we call it as glycerol. Okay. Now here I have ethane 1,2-diol, and here I have propane 1,2,3-triol. Clear? Okay, next let's move to phenols and its nomenclature. So if you have simple OH group, then we call it phenol. If you have a CH3 group attached, then we call it as 2-methylphenol or orthocresol. Now here also the common name is very important. This is metacresol or 3-methylphenol. This is paracresol or 4-methylphenol. Now, dihydroxy derivatives are 1,2,1,3 and 1,4-benzene diol. Okay. Now, 1,2 is what called as catechol, 1,3 is called as resorcinol, and 1,4 is called as hydroquinone or quinol. Okay. Fine. Now we'll talk about ethers and their naming. So see, you have ROR. Okay. It is named as alkoxy alkane. Okay. Now this alkoxy should stand for a R group. Okay, which one? Which is having lesser number of carbon, and this alkane should stand for that R group which is having more number of carbon. I'll give you an example. So for example, so here when you have same number of, if it is a symmetrical ether, then it is simply methoxymethane. This is ethoxyethane. But now here if you see this side I have one carbon and this side I have three carbon. So it is methoxypropane. You can see one methoxypropane. Okay, the main name will be on the carbon which is having more number of carbons. Next here you can see you have C6H5 and OCH3. So this is methoxybenzene, or the common name is anisole. Then here also you can see it is ethoxybenzene, right? Then you have here you can see the long chain is there of 7 carbon, and here you have 6 carbon. So here this one will be the main chain and the name will be like phenoxyheptane. Okay. Next here you can see 1, 2, 3. So you can have 2-methoxypropane. Okay. Next we have this particular 1, 2, 3, 4 and 5, and this side I have 6 carbon. So obviously this will be acting as a substituent. So you can write down 3-methyl, I can write butoxybenzene. Okay. So like this we can name the ethers as well. So after this, we'll be studying about the structure of alcohols, phenols and ethers. Now see, alcohols, phenols, ethers, the structure is like this. We have here lone pairs of electrons are present on oxygen, right? So what happens because of this lone pair? Okay, actually if you see the geometry is sp3 hybridized, right? And the bond angle should be 109 degree and 28 minutes. Right, that is the original value. But due to this lone pair, what happens? There is repulsion. Okay, so what will happen? They will repel each other. Then these will repel this one, and the bonds will slightly come closer to each other. And in alcohols, the bond angle is less than the actual value. How much less? It is actually 108.9 degree. Okay. Now in phenols, what happens? Since this is a planar molecule, the angle almost remains as 109 degree. The interesting part is in ethers. Now see, in ethers what happens, you can see that here I have two bulky groups, right? So ethers are written like this. Now see, these two are highly bulky groups, so they repel each other. If they repel each other, suppose this is there, they repel each other, they move far away from each other, and this bond angle is more than the original value. How much more? 111.7 degree, 111.7 degree. So how can you arrange the bond angle? So first will be ethers, then we have phenol, and then we have methanol, or you can write alcohols. Clear? Okay, now we'll talk about preparation of alcohols, how we can prepare alcohols. So children, for learning, you see there are 4 organic chapters, there are so many reactions. So to do active recall, to remember, you must write down the reactions in a structured way, in the form of mind maps, in the form of the what I'll say, in the form of schematic diagram, so that you can recall it. So I will draw here for preparation of alcohols, and I want all of you to pause this video and draw it right now with me. Okay, so first of all, how we can prepare? The first method is from alkenes, second is from carbonyl compounds, and third is using Grignard reagent. Okay, remember how we can prepare. The first one is from alkenes, second is from carbonyl compounds, and third is using Grignard reagent. Now from alkenes you have two methods: further acid catalyzed hydration and hydroboration oxidation. Next, from carbonyl compounds you have reduction of aldehydes and ketones and reduction of carboxylic acid and esters. And lastly, I have from Grignard reagent. Okay, so now let us understand the first method, that is from alkenes. Now see, from alkenes, this is the first method, from alkenes. Okay, so what will happen if you add H plus and water? Okay, water if you add in acidic medium, so H and OH are added to the double bond. The double bond breaks, H and OH are added, following here Markovnikov's rule. Okay, now similarly BH3 H2O2 OH minus, the hydroboration oxidation part, this also add H and OH minus following anti-Markovnikov's rule. Okay, now I'll give you an example. Suppose I have propene. Okay, CH3 CH double bond CH2. Now if you add here H plus with water, so what will happen? H and OH will be added following Markovnikov's rule. Now what is Markovnikov's rule? The negative part here, what is the positive and what is negative? H plus is positive, OH minus is negative. So the negative part will attach to the carbon having less number of hydrogen. Here I have one hydrogen, here I have two hydrogen. So the negative part will attach on the carbon having one hydrogen. Okay, so what I will get? CH3 CH OH CH3. The product here is propane to OL. Okay, now if you do the reaction by addition of BH3 whole to H2O2 OH minus. So if I do this, it will add H and OH following anti-Markovnikov's rule. So I have CH3 CH2 CH2OH, which is propane 1OL. Okay, so now you can see that you will get one propane 2OL and another propane 1OL. Okay, so this is anti-Markovnikov addition under hydroboration and oxidation, and this is Markovnikov addition using H plus and water, or acid catalyzed addition of water. Now coming to the next one, that is using aldehydes and ketones. So reduction of aldehydes and ketones. So for that we have two reagents. One is H2 palladium, another is NaBH4. So for example, you have CH3COCH3. Okay, or I'll just write down the correct structure so that we can understand. So what will happen here? See, CH3 C double bond O, CH3 is there. Now if I add here H2 with palladium, so what will happen? CH3 CHOH CH3. Okay, and this particular compound, okay, this one you can also treat it with NaBH4 to give you the alcohol. Now similarly we can also use acids and esters. So if you have acids and esters, the reagent used is LiAlH4 and hydrogen or hydrogen palladium. Now coming to this one is your Grignard reagent. Okay, so if you treat Grignard reagent with carbonyl compounds, okay, then you will get alcohols. Okay, this is one of the most important reaction, and let us understand that with an example. So suppose I have CH3COH, okay, and you are treating it with CH3MgBr. Now see, understand the structure of the Grignard reagent. The Grignard reagent structure is like this. RMgX is there, right? So R is minus and Mg is plus, right? So this R behaves as a nucleophile, and in carbonyl compound, the C is an electrophile. Okay, the carbonyl carbon is an electrophile. So this one will attack here and this one goes up. So you can see here this is minus, this is plus, and here this is minus, this is plus. So here OMgBr will form and C will bond with CH3. Now when OMgBr is formed, it will undergo hydrolysis to give you final product CH3, CH, OH, CH3. Okay, so that is propane 2OL. So like this, using Grignard reagent, we can prepare the alcohols. Clear? So we have 4 methods we have understood. Now you can see from this one, we can just let us have a quick revision based on this table. Okay. So from acid catalyst, what is the reagent I have to use? H2O, H plus, and this and follows Markovnikov's rule. Now, if you have hydroboration oxidation, here we have BH3 whole 2, then we have H2O2, OH minus, okay, and this follows anti-Markovnikov's rule. Next, from carbonyl compounds, it is reduction of aldehydes and ketones. So here the reagent used is your NaBH4, okay, or hydrogen nickel, right? Similarly, for carboxylic acid, we have lithium aluminium hydride or or hydrogen nickel. Next, from Grignard reagent, you can treat Grignard reagent with carbonyl compounds. Okay, that will give you the alcohols. So this is all the methods of preparation of alcohols. Now let's move to the methods of preparation of phenols. Okay, so for preparation of phenols, we have different methods. The first one is from haloarenes. Next one is from benzene sulfonic acids, then from diazonium salts, and last one is from cumene. Okay, so first let's see from haloarene. So we have already studied the first method, this one. Yeah, the first method here from haloarenes. Now we have already studied this one in the haloalkanes chapter. Okay, if you remember, under very strong conditions of high temperature, high pressure, if you treat it with NaOH, we will get OH, right? This, if you would remember, if you keep adding electron withdrawing groups, the temperature comes down, right? Next one is from benzene the next one was from benzene sulfonic acid, right? So this is your from benzene sulfonic acid. Okay, so how to produce this benzene sulfonic acid? So first of all, you can take benzene, which is and if you treat it with oleum is nothing but concentrated H2SO4. Okay, so if you treat it with concentrated H2SO4, you will get SO3H, and then if you just hydrolyze it, NaOH and H plus, you will get OH here. Okay, next one was from cumene, right? The third one is from cumene. Now cumene is nothing but this compound which is isopropyl benzene. Okay, now if you add oxygen here, what happens? 2 oxygens are added. Okay, now once this is there, if you just hydrolyze it, here phenol will be there, and the byproduct produced is acetone, which is asked in the question, so keep this one in mind. Next, the fourth one is from amines or from benzene diazonium chloride, right? So I'm writing here from amines. So first of all, amines are converted to benzene diazonium chloride, and then if you just treat it with warm water, this whole group will be replaced with OH group. Clear? Okay, so 4 methods of preparation of phenols. Now we will go to understand their physical properties. So basically these alcohols, first if I talk about their boiling point, these alcohols have very strong hydrogen bonding. Okay, now when they can form very strong hydrogen bond, their boiling point, the intermolecular forces are very strong and it is difficult to evaporate them. So the boiling point is generally high. Okay, but increase in the number of carbon, so if the size increases, the boiling point will also increase. Okay, decrease with the increase in branching, same as haloalkanes and haloarenes. If the branching increases, the boiling point will decrease. Now coming to solubility. Okay, due to their ability to form hydrogen bond with waters, they are highly soluble in waters. Next, the solubility decreases with the increase in the size of the R group. Okay, because this is the hydrophobic part. If the R group increases, the it it produces hindrance in the formation of hydrogen bonds, as a result of which the solubility decreases. Clear? So now we will move and discuss about the reactions of alcohols. Okay. Now before starting the reactions, we have to understand that alcohols can behave as both nucleophiles and electrophiles. So if alcohols are behaving as nucleophiles, they can react with electrophiles, and if alcohols are behaving as electrophiles, they can react with nucleophiles. So let us see how these alcohols are behaving as nucleophiles and electrophiles. So first we'll talk about how alcohols are behaving as nucleophiles. So the alcohols contain this lone pair on the oxygen, right? And this lone pair on the oxygen makes it nucleophilic, and then it can attack on any electrophilic species like carbocation. Okay, so we'll get this type of compound, and then there we will get a product like this. Okay, next, how alcohols can behave as electrophile. So whenever you have an alcohol in an acidic medium, this OH group attacks on that one, and the OH group gets protonated. And once it gets protonated, now the carbon to which this OH group is attached, this is highly electrophilic in nature. Okay, so any nucleophile can now attack on this one, and this OH2 will go out. Okay, so these are the two criteria you have to understand, that it can behave as a nucleophile, it can also behave as an electrophile. So now let us see the reactions of alcohols. So when we have, so okay, one more thing I just want to point out here. So if you see in the nucleophilic, like where alcohols are behaving as a nucleophile, there is cleavage of OH bond. The bond between OH is broken. Okay, when alcohols are behaving as nucleophiles, the OH bond will break, and when the alcohols are behaving as electrophile, okay, in that case this bond is breaking. You can see here this bond is breaking, right? So when it is behaving as electrophile, CO bond will break, and when it is behaving as nucleophile, OH bond will break. This is important, keep it in mind. So now you will understand. So when I'm talking about cleavage of OH bond, so exactly we are talking when alcohols are behaving as nucleophiles. Okay, and now when cleavage of CO bond is there, so these are those reactions where the alcohols are behaving as electrophiles. Okay, sorry, electrophiles. So now let us see what all reactions we have in the first part and in the second part. So when alcohols are behaving as nucleophiles, or where there is cleavage of OH bond, we have reactions with metals, acidity of alcohols, esterification. Okay, and for the cleavage of CO bond, there we have reaction with HX, reaction with PX3, dehydration and oxidation reactions. So let us understand one by one. So first we will talk about those reactions where there is cleavage of OH bond. So first one, if you see, that is reaction with metal. Reaction with metals. Right. So here this ROH can react with Na. Okay, it is like, see, this one will donate a H plus. OH bond will break, so it is donating H plus. So literally it is behaving as an acid. So when a metal reacts with acid, what do we get? Salt plus H2 gas. So the same thing. Here you will get the salt and H2 gas. The second is the acidity, about which I'll be discussing later. The third one is esterification. So alcohols can form esters by reacting with carboxylic acid, anhydrides, and even with acid chlorides. Okay, so ROH plus RCOR. So you have to see, from here this bond will break, and from here this OH bond will break. Okay, so what will be the group? R, O, and this O, then C, this R. Okay, so you have ROCOR dash. Okay, similarly here also with anhydrides, and it can also form esters with acid chlorides. Now we will talk about the reactions where there is cleavage of CO bond. Okay, the CO bond should break. Okay, means it is behaving as electrophile. Okay, so under that, if you have seen, the first reaction was reaction with HX, then we have reaction with PX3, then we have the dehydration reaction, and then we have oxidation reaction. 4 reactions were covered here. So the first reaction, that is reaction with HX, right? Reaction with HX. So here what is the mechanism of reaction? See, understand, ROH is there and you have HX, right? So in HX, H plus is there, so this O will attack on this one, and this one first gets protonated. Okay, now if you see that in HX, this X minus is also produced, so that will attack here, and this H2 will go out, and you will have RX plus water. Okay, so that is why you will get RX plus water. Now this, we have a particular reagent called as Lucas reagent. Okay, from here questions are asked repeatedly. So remember, what is Lucas reagent? It is HCl with anhydrous ZnCl2. Okay, now what will happen if your alcohol is tertiary? Okay, then reaction will take place immediately. Okay, and you will find turbidity. Your solution will become dense, or I can say translucent, which did because of the precipitation formed, and you will find a turbidity. The solution will become denser. If it is a secondary one, what will happen? The reaction will take after 5 minutes. Means the turbidity will occur, but after 5 minutes. But if it is primary, okay, then there will be no reaction. So in this way, using a Lucas reagent, we can separate, or we can identify primary, secondary and tertiary alcohols. Okay. Now the second one is the reaction with pX3. So this we have studied in the haloalkanes chapter also. So you will get Rx plus H3PO3. Okay, next the third one is dehydration reaction. So if I use concentrated H2SO4 at 443 Kelvin, it will remove water molecule and you will get alkenes, and the order of dehydration is 3 degree, 2 degree and 1 degree. Okay, now if these alkenes are formed, also remember it is formed using Saytzeff rule. Clear? Okay, now we will talk about the oxidation reaction. Okay, the another reaction which is oxidation reaction. Okay, now oxidation can be done on various purposes, or by using different reagents. So the first reagent for oxidation is CrO3. Now here, if you have primary alcohol with CrO3, you will get aldehyde, and if you have secondary alcohol, then with CrO3 you will get ketones. Okay, now the second reagent which is used is PCC. Now PCC will convert primary alcohols to aldehydes. Okay, here also remember, primary alcohols will get converted to aldehydes and secondary alcohols will get converted to ketones. Okay, now here we will understand one more important thing, that if you have an alcohol, so especially primary alcohol, with mild oxidizing agent like PCC, they will convert to aldehydes. But if these alcohols are directly converted to acids, for that we need strong oxidizing agent like KMnO4 or K2Cr2O7. Okay, and if you use mild oxidizing agent, you will get RCHO, and here also I can use mild oxidizing agent. Now for RCOOH to convert to acid, means the reduction, the above one is oxidation. If you want to get from RCOH to RCH2OH, that is from acids to alcohols, you have to use strong oxidizing agent, reducing agent like lithium aluminium hydride. And similarly, from RCHO to RCH2OH, means aldehydes to alcohols, we have to use NaBH4. Okay, so this chain you have to remember, it is important. Next reagent is copper at 573 Kelvin. So it converts primary alcohols to aldehydes, secondary alcohols to ketones, and tertiary alcohols to alkenes. Okay, so that you have to remember. So with this, we are done with the reactions of alcohols. Now let us see the reactions of phenols. Okay, so phenols, we have these reactions. The first one is acidic nature, again about which we will discuss. I have skipped the acidic nature so that I can discuss both for phenols and alcohols together. Next, we will talk about esterification. Then we'll talk about electrophilic substitution reaction, where we will talk about nitration and halogenation, then Coles reaction, Riemann-Tiemann reaction, reaction with zinc dust, and then oxidation reaction. So we have how many reactions? 1, 2, then 3, 4, 5, 6 and 7 reactions we will study. Okay, so let us start here. The first one is the acidic nature. Okay, so under acidic nature means how can you prove that something is acidic? So if it can react with metals, okay, then we can say that it is acidic in nature. So that is why the first reaction here is the acidic one, acidic nature. Okay, where we are showing the reaction with Na, and the second reaction is with NaOH. Okay, so with Na it will give you salt plus H2, and with NaOH it will give you salt plus water. Okay, now second one is the esterification, about which we will study at the end again, at the end of this one. The third reaction that was there in the list was electrophilic substitution, right? And under electrophilic substitution we have nitration and hallucination, right? So nitration, listen, if you use dilute HNO3, you will get NO2 and at ortho and para product. Now remember, OH is a electron withdrawing group, so it is ortho para directing. Okay, now this is concentrated HNO3. Okay, so that will add NO2 group to all the ortho para positions, 2, 4, 6 trinitrophenol. Okay, next we have this one, that is hallucination. Okay, hallucination reaction. So if you use simple only bromine water, so all the ortho para positions are occupied. But if you use bromine with CS2, okay, that will add bromine at ortho and para positions separately. So here bromine will be added at ortho positions and here bromine will be added at para position. Okay, so now this is over, and the fourth one is your Kolb's reaction. Okay, so in Kolb's reaction, what happens when you take phenol and treat it with NaOH? First you will get a salt, and then if you treat it with CO2, you will get OH, and this, the ortho position, gets substituted with a COOH group, and this particular compound is called as salicylic acid. Okay, now we will continue with the fifth one. Okay, the fifth reaction here is the Remer-Tiemann reaction. Okay, Remer-Tiemann reaction. So here what happens, first we take OH and treat it with CHCl3. So we get a salt here, and the CHCl2 is substituted at the ortho position. Then again when you treat it with NaOH, what will happen? Both the chlorines are replaced with OH group, and then there is dehydration and you get CHO group. Okay, next with hydrolysis you will get OH and CHO group, and this particular compound is called as salicylic aldehyde. Okay, so this is the fifth reaction. Now sixth reaction is the reaction with zinc dust, that will give you benzene simply. And the seventh reaction is the oxidation of benzene. If you treat it with Na2Cr2O7 and H2SO4, you will get benzophenol. Okay, so we have left one reaction, that is the esterification reaction. So esterification reaction is similar to what we have studied in the alcohols one. So what are the ways how we can do esterification? You can treat the alcohols with carboxylic acid or acid chlorides or anhydrides. Okay, so you can see here phenol, so I have put like this so that any of the carbon can be attached, so that actually means. And when you treat it with RCOH, you will get OCOR and water. If you treat it with anhydride, so you will get OCOR with the carboxylic acid. And if you treat it with this one acyl chloride, you will get OCOR and HCl. So you will get ester and HCl, ester and carboxylic acid, and ester and water. Now if you have salicylic acid and if you treat it with acetic anhydride, so there will be esterification. So you can see that this OH group will get converted to this one, that is ester, and this particular compound is called as aspirin. Okay, or you can call it as acetyl salicylic acid. Okay, one more thing, I think, yeah. Okay, so this is important reactions of phenols. Now we will understand the acidic nature of alcohols and phenols. Now there's a basic rule here: if you have electron withdrawing group, acidity will increase, and if you have an electron donating group, the acidity will decrease. It's the first thing. Next, you always have the resonance effect is more powerful than inductive effect. Okay, this is point number 1 and this is point number 2. Next, third thing, the third thing is ortho and para positions will have more impact than the meta position. Okay, now let us understand this with an example. Suppose I have OH with NO2 group. Okay, let me take an example like this. You have OH with NO2 group here, and you have OH with NO2 group here, and you have OH with CH3 group here. Okay, now see, first of all, if you see, this is electron withdrawing group, this is also electron withdrawing group, and this is electron donating group. So donating group will decrease the acidity. So if I number it as 1, this is as 2, and this is as 3, so 3 will have the least acidic nature. Now if you compare 1 and 2, now at the para position, the effect is more predominant, so that is why this one will be highly acidic and then one will be least, like in between 2 and 3. Okay, so this is what these three things you have to remember for acidic nature, and while solving questions we will do more questions on this. Now let's move to some commercial alcohols, and the first one we'll talk about is methanol, whose formula is CH3OH. Okay, now there is a very important term here. Methanols are also called as wood spirit, and it is used in the distillation of wood. Now how it is this prepared? So if you take carbon monoxide and treat it with H2 in presence of ZNO and Cr2O3, you will get CH3OH. And here are some uses of this one: colorless liquid, poisonous in nature, and it is used in solvents, as solvent in paints, varnishes, and it is used for making formaldehyde. Now let's talk for ethanol. Ethanol structure is CH3CH2OH. Okay, how it is prepared? So when you have any sucrose, okay, sucrose with water will give you glucose and fructose. Okay, now this one, the glucose one, will be converted to zymase to give you alcohols and carbon dioxide. Now this one, that is the enzymes you should remember. Okay, enzymes you must remember that from sucrose to getting glucose and fructose we need invertase, and then from glucose to alcohols and carbon dioxide we need zymase. Okay, so this is a colorless liquid, poisonous in nature. It is used in paints, varnishes, and chiefly for making formaldehyde. Okay. Now moving forward to the ethers preparation. Okay, how are ethers prepared? So the first method of preparation of ether is by dehydration of alcohols. Okay. So if you take alcohols and treat it at 443 Kelvin with H2SO4, you will end up in getting alkenes. But if you take alcohols and treat it with H2SO4 at 413 Kelvin, you will get ethers. Okay, so what is the mechanism of formation of ether? So first step is what? The OH gets protonated. Okay, you'll get O plus H2 formed. Now after that, the another alcohol molecule, since now this is O plus H2, this carbon is electrophile in nature, so another OH group can attack on this one and you will get a product like this. And in the third step, there is deprotonation. This OH group comes out and you will have this H plus out and your ether is produced. That is first method. The second method is called as Williamson ether synthesis. Now here what you do, you take one haloalkane and one alkoxide ion. Alkoxide means R dash ONA. Okay, now see, in Rx this is delta minus and this is delta plus, and here I have negative charge, so this one can attack on this one. Okay, so I will get R O R dash plus NaX is formed. Now this is the ether. But here one very important rule that you must remember is the Rx must be a primary halide. Okay, the Rx which you are taking, that must be primary. So for example, if I want to prepare this particular ether, there is a combination that this group CH3Br should be there and this whole thing should be part of the alkoxide ion. Then this negative charge can attack on this one and the Br will be out. Okay, and you will get NaBr. Clear? Okay, next we'll talk about the physical properties of ethers. The CO bond in ethers are polar and thus the ethers have a net dipole moment. So if you see the structure of ethers, it is like this, right? So here there will be attraction and here also there will be attraction. So there will be a net dipole moment. Ethers are soluble in water because of their ability to form hydrogen bonds with water molecule. So since oxygen has lone pair, it can form hydrogen bonds, because of which they are soluble in water. Now we'll talk about the chemical reactions of ethers. So here the first reaction is cleavage of CO bond and the second one is electrophilic substitution, where we'll study about halogenation, nitration and Friedel-Crafts alkylation. Okay, so these reactions are very common, we have already studied, we'll just see them. But this cleavage of CO bond is a super important reaction. Okay, and questions will be asked from here, mark this one. Okay, questions will be asked. Every year it has been asked from this one. So this is very important and we will understand in detail. So first let's understand the mechanism, what happens when you treat a ether with HX. Okay, so what happens is the oxygen lone pair, okay, attacks on the H and you get a protonated ether. Okay, now what will happen, the X minus, okay, so I'll draw this one like this, R1 O plus H R2. Okay, now this X minus will attack on one of them. Okay, so let us assume that X is attacking on R2. So this bond will break and we will get R1OH plus R2X. So now understand what happening here is this X minus is attacking on R2. But how will we know that whether this X minus will attack on R1 or R2? What is the logic? Anything is there that determines? Yes, it is there. What is that? Let us understand. Now see, if you have this R1 O R2, okay. Now see, if the R1 or R2, any of them is either primary or secondary, then the reaction follows SN2 mechanism. If it follows SN2 mechanism, then X minus will attack on the less hindered side. Clear? Okay, with example it will be clear, don't worry. Now if any one of them is either a tertiary or the carbocation is resonance stabilized, then SN1 reaction will follow and X minus will attack on the side of more stable carbocation. Okay, so let's see one example here. So this is a structure you can see. Suppose question number 1, you see here I have CH3O C, CH3, CH3 and CH3. Okay, now first step, what will happen? There is protonation, so O plus will take place here and H will attack here. Now there is I minus, right? Where will this I attack? Now if you see this side, okay, this side is tertiary, okay, so obviously I minus will attack on the tertiary side because this group is tertiary, so reaction mechanism followed is SN1. So what are the products that I will get? The products will be CH3OH plus CME3 and here you have I. Okay. Now let's talk about when you have a phenol O and CH3. So whenever there is a benzene ring attached, obviously the bond will always break on this side, okay, because we know here there will be resonance. This has a partial double bond character, so this bond cannot break, so this bond has to break on the other way. So here there will be O plus H, means always the product will be phenol, okay, and the other product will be CH3I. Okay, now let's see this one. You have cyclohexyl, okay, OCH3 and here you have HI. Now see, this side is secondary and this side is primary. So if it is secondary, what will happen? On the secondary side and primary side, the reaction will follow which mechanism here? SN2, and I minus will attack on the less hindered side. So I minus, this is a smaller one, this is less hindered. So you will have phenol here. Sorry, not phenol, cyclohexanol. Okay, this is not phenol. If phenol, if there is O means benzene ring is there, then always the bond will break here and H will come here and I will come here. Okay, so here I'll get cyclohexanol and CH3I. Okay, so this is how the cleavage of ethers takes place in presence of HI. Now next one, we will see the electrophilic substitution reaction of ethers. Now let me just tell you that this particular product is called as anisole. Okay, now the first one we'll see here is halogenation. Okay, so if you use bromine with acetic acid, now OCH3 is a electron donating group, right? So it will direct in ortho-para direction or ortho-para points. So you will have the product here like this. Sorry, yeah, you will have the, sorry, one second. Yeah, here I'll get the product like this, where I will have OCH3 and you have bromine in the ortho position and you have OCH3 and you have bromine in the para position. Next, RCOCl, this is your Friedel-Crafts acylation. Okay, so that one will add here OCH3 and this one will add COR at the ortho position and here you will have OCH3 and you will add COR at the para position. Next you have RCl and AlCl3. This is your Friedel-Crafts alkylation, right? So here what will be the products will be forming again at the ortho para position. So you will have OCH3 and here you will have R, and another product that is there is OCH3 and R here. Next we'll have nitration. So here you will get nitration for OH and sorry OCH3 and NO2 is at ortho position and you have one more OCH3 group, and you have NO2 at the para position. Okay, so this is how the products will be formed. Very simple, reagents are constant. Just you need to remember that OCH3 is a ortho para directing group. Okay, so students, that was the end of this chapter, and we have discussed all the reactions that is there in this particular chapter, and mechanisms I have not discussed, because in the next video which is coming about the most important questions from this chapter, there will be talking about the mechanisms in detail. Okay, so if you have liked this video, so please subscribe the channel. And one more thing is, if you want the like PDF of these notes and everything, please join our WhatsApp channel. The link is there in the description section, and you will be getting all these PDF notes so that you can revise them during your exam. Thank you so much for watching, and yes, do not forget to hit the subscribe button.